All right, lesson 2.8. Our last lesson before our midterm for unit 2. And so as we get started, what we're going to learn about today is function inverses. So inverse, now this is a really cool deal. In math, everything has its opposite. So for example, the opposite of adding would simply be subtracting. So let's just do the operation. How about this? I'll title this, you have your operation over here, you have your operation over here, and you have your opposite operation. And so everything in math has its opposite. So in the case of adding, it would be subtracting. Let's say you were multiplying by 3. Well, the opposite would be to divide by 3. Everything has its opposite. Well, when it comes down to an inverse, what that is the opposite of a function. So last class we learned in 2.7 that you can apply one function to another inside of a function composition. So what we're going to learn today is that if you apply some function, well, the opposite of a function is its inverse. It's the opposite that cancels out one another. So first, not every function will have an inverse, number one. But if a function does have an inverse, we're going to learn how to solve for it and state any restrictions if necessary. That's the point of today's lesson. So here in the paragraph form, this will explain what I just said, that an inverse relation is an expression that will map a member of another relation's range back to its domain. It just does the opposite. Instead of a domain going to a range, like normal, input becoming output, the output will become the input, or the range will become the domain. They cancel one another, okay? So mathematically, if y equals f of x, then its inverse, what happens is instead of x mapping to some y value, the y value will map to the x value as shown here. The y value will map to the x. So if x originally maps to the y, now the y maps to the x. So they undo each other. So it's kind of like this. They're just going around and around. That's an inverse. Shown using compositions, if f and g are inverses of one another, then f of g of x will equal x. They'll just cancel each other out, and all that's left is whatever number you originally plugged in. So every inverse relation can be found by switching each x and y variable and then isolating the new y variable. That's going to be our algebra step to solve. So as you can see here, we switched. When we switch here, we just name the function something different. Usually we'll write f with a little power of -1, but in this case it was a g. So with that, how can you know if an inverse function exists? Well, given a function, usually to determine if a graph itself is a function, we have what's called the vertical line test, where you check to see, can this function pass the vertical line test? If so, what that means is every member of the domain has one and only member of the range. So this is the function definition I'm giving you right now. Okay, so back in Algebra 1, you learned that a function exists when every member of the domain has one and only one member of the range. And we tested that with a vertical line test. Now that's how we determined if something was a function. We used that little test there. Let me add this down. Okay, so that's how you determine if something was a function, was a vertical line test, because what that does is, notice I'm cutting through the x-axis here. I'm checking to make sure every x value along the graph has only one location, only has one and only one y value. Well, for an inverse function, you don't use a vertical line test, you use a horizontal line test. Because what that's going to do is it's going to check to see if every member of the range has one and only one member of the domain. So that's for a function test. Let me put this here, a function test. Because to be a function, actually no, to be a function, it's a function when every member of the domain has one and only member of the range. An inverse exists. Let me just copy this over. An inverse will exist inverse will exist, whoops, when every member of the range has one and only one member of the domain. That's the inverse test. An inverse will exist when every member of the range, that means y values, has one and only one member of the domain. Now, I want you to know that though that's a true way of thinking about it and looking at it, that won't satisfy any test questions you would need to not just put the horizontal. What I'm saying is you can't just say the passes a horizontal line test. This is the definition you need to know right down here. Just as in Algebra 1, they would say this is the definition you needed to know for a function. For pre-calc, this is the definition you need to know for an inverse. That's that every member of the range has one and only one member of the domain. That's the definition you need to know. Okay, so the steps to find an inverse function. As I said earlier on, you can determine if it exists by using the horizontal line test. That's what I just walked through, checking to see if every member of the range has one and only one member of the domain. You replace or you interchange, it says here, you switch x and y. Here we'll use the terminology f -1. That means inverse of f when you see that. And then we'll solve for the new y. There's your steps right there. You can look back at that later. So with that, I'm going to walk you through. First, given a table. It says find the inverse relation of the given table. Well, to do this, what you're going to do is just switch your x and y. It's as simple as that. So if this is the original function, or they call this a relation, if this is the initial relation, this is the inverse relation. Is you would switch these. So -1 becomes and a 1. Those two switch. These two switch. It becomes a 2 over a 3. Now a 0 and a 4 and a 2 and a 6. Now over here, this was a function because each and every x has one and only one y member. Each and every x has one and only one y member. But the inverse is not a function. This is not a function. Now the reason I knew it was not a function is because two y values here have different x values. Each member of the range has to have one and only one member of the range or domain for an inverse. Well, this has a domain value of 3 and a domain value of 6. Therefore, the inverse is not a function. And if you see down here, you'd see the two x's produce different y's. So it's not a function. Okay, so that test that I was giving you, you test on the original relation, not on the inverse itself. So here, the original table is a function because each x value has exactly one y value. Each x value has exactly one y value. However, the inverse is not a function because so if you're talking about the inverse itself, you would say the value of 2 is mapped to 3 and 6. Therefore, using this as the domain and this as the range, each member of the range does not have one and only one member of the domain. Or if you just tested the inverse using the Algebra 1 test, once looking at the inverse, you'd say, well, it's not a function. This inverse is not a function because each x, the 2's, do not have one and only one y value. Okay, so now let's take a look at example 2 here. All right, on these different representations, what we're going to do is find if the inverse exists. So again, what you're looking for originally to be a function, each member of the domain has to have one and only one member of the range. So each value here can only have one y value attached. So -5 has 0, -2 has -1. Notice this is good. What would make this not original, the g itself be a function, is if one of the values had two y values. So like 0 pointed at 0 and 0 pointed at 7. Now g would not be a function. But that's not the question here. The question is, does the inverse exist? And so what you're looking for now, does each and every member of the range, does each y have one and only one x value attached to it? And the answer is yes. So G inverse exists. And since it exists, we would switch. And again, I'm going to put these in numerical order. -3, -1, 0, 4, 7. And I'll put these in numerical order. -5, -2, 0, 1, 3. But what happens with the inverse is the domain and range have become opposites. So instead of -5 mapping to 0, 0 maps to -5. Instead of -2 mapping to -1 maps to -2. Instead of 0 mapping to 7, 7 is going to map to 0. Instead of 1 mapping to -3, -3 is going to map to 1. And finally, instead of 3 mapping to 4, 4 is going to map to 3. So the inverse does exist. Okay, over here, again, to be a function itself, every member of the domain has to have one and only one member of the range. Well, now I'm looking to see, does each member of the range have one and only one member of the domain? And the answer is no. 10 does not have a member of the domain here. This member of the range does not have a member. So you would actually say that f -1 of x does not exist. Since 10 does not have one and only one member of the domain. Okay, so I'm just going to leave this one blank. It is a relation, so you could relate the two back, but 10 would not have one. Now, if 10 wasn't there, then yes, you would go forward because each member of the range would have one and only one member of the domain. Okay, so with that, I want you to try, if my board cooperates here, the first DOL number 1 on the back of the packet. Go try that. Give you a moment, pause the video and try that. Now let's take a look at example 3. So in example 3, the function f is shown. And we want to know, is the relation of f a function? So to determine if something is a function, you would first look to see if it passes the vertical line test. So I'm going to use this dashed red line, the vertical line test. And what this does is it checks to see if every member of the domain, that's the x values, has one and only one range value. So I'm looking to see, does this graph ever hit this line more than one location at any one time? And the answer, I know right there, it's really kind of close, but the answer is this is a function because it passes since it passes the vertical line test, we know it's a function. Now for AP Pre-Cal, the answer you're going to be looking for is this, f is a function. F is a function since every member of the domain has one and only one member of the range. Okay, so that's the definition of a function. So that's the first test here. Now the second is, will the inverse of f be a function? And to just know for a fact, let's use the horizontal line test. And what we can see is no, this will not be, and the inverse will not be a function. So the inverse of f will not be a function. And you cannot just say because it fails horizontal line test, that will not give you credit. What you need to say to get credit is the inverse of f will not be a function since every member of the range does not have one and only one member of the domain. That's why the inverse does not exist. Okay, so there's my first answer here, second answer right there. Now we're going to graph the inverse. This would be called an inverse relation. And the way you would do that is you would just switch x and y. You'd find some points. So I'm going to look and see, try to find the best points possible. I have this point here, which would be 0, 1. The inverse for that would be at 1, 0. Right there, 1, 0. I just switch my x and y's. This point is approximately, let's see, -1, -2, -3, -4, -5. 1, 2, 3, 4. So I'm going to say -5, comma, I'll call that 3.8. And that's where that arrow is. So now I'm going to go to 3.8. 1, 2, 3, almost 4. And then -5. Which takes me down here to that point, and that's going to be my arrow. Okay, my arrow is going to go through that point, so that's at 3.8, comma, -5. That's going to be the arrow of my graph. So it'll go like this, through there. And then the parabola here See, it has a maximum point here, which is 2 to the right and 4 up. 2 to the right and 4 units up. That means over here it'll be 4 to the right, 1, 2, 3, 4, and 2 units up. That's going to be the top of my parabola. And then this point of the parabola is going to be 4 to the right and 1 up. So I need to go 1 to the right and 4 up. 1, 2, 3, 4. That's going to be the end of that parabola. 1, 4. I didn't write this point's location. 2, 4, comma 2. So let me find my parabola tool. And now that last arrow, see how it goes up and to the right? Well, the right becomes up and the up becomes right. And so this arrow will still go just about 1 up, 1 right from here. It'll be very similar, but instead of going, this one went a little bit higher than it did right. Now it'll go a little bit more right than it did higher. So it'll be something like that. And that would be your inverse relation. This would be an inverse relation. I want to hit that word. It's not a function because, so you can see over here, it would fail the vertical line test. This is an inverse relation, which a relation just means it's relating the x's and y's together, but it doesn't pass the function rules. All right, now I want you to try DOL number 3 in the back of the packet. All right, now let's take a look at example 4. Part A says, is the function of f of x equals x squared minus 3 a function? Why or why not? Well, if you think about this as a graph, x squared, you need to know your shapes in AP Pre-Cal. The graph of x squared, I go ahead and label this. Here's y equals f of x. This is my x-axis. If you plug in, you could plug in values, but x squared is going to look like a parabola. So let me go back to my tools. I just found this one a moment ago. Here is my parabola, like that. So the graph of x squared is going to look like a parabola. Now, we have a transformation. That minus 3 is going to shift the graph to translation. And because it's on the outside of the square is what determines the shape. Since it's on the outside, that's a vertical translation, which is a truth teller. It goes down 3 units. So this would be a parabola that would look something like that. Okay, so here's my parabola that I'm going to put, and this would be down 3 units. Okay, we were able to get that without a calculator. That vertex there would be 0, negative 3. Now, is this a function itself? Yes, that is a function. It passes the vertical line test. Now, is its inverse going to be a function? No, it would fail the horizontal line test. Now, that's not reasoning. That is not reasoning for AP Pre-Cal. I want you to know that. Even though we can see here that it fails the horizontal line test, I'll go ahead and write it fails the horizontal line test, so HLT. Even though it fails the HLT, that does not satisfy AP Pre-Cal for grading. You need to know the true definition. And so what I would say here is the inverse of f is not a function since every member of f's range does not have one and only one member of the domain. And when I say have, you could say is not mapped as well, if that makes more sense to you, since every member of f's range does not map to one and only one member of the domain. You could use that terminology as well if that makes more sense to you. Okay, so whatever makes more sense to you, go with that. But that's the idea there on why it's not a function. So this is not function, so I'll go ahead and circle the why not. Okay, now find the inverse of f if its domain is restricted. Now, what does that mean? So on this graph, if you restrict the domain, what that means is if you come in here and you said, okay, we're going to cut off this graph to where we only go from 0 to infinity. So anything outside of that gets cut off. So if you cut off all that, now we would pass the horizontal line test. Noticing that, okay? So what I'm going to do here is I want to be sure in the future we can see that part of the graph. So I'm just kind of line it like this. If we said this is restricted out, that part is restricted out. If I restricted that out, what would be the inverse relation? Well, here's how the algebra comes in. So if I f of x represents the y, what I would do to solve this is I would say x equals y squared minus 3. And from here, you just solve for your new y. So I switched x and y. And that was the first step. Switch x and y. Let me do this in purple here. The first step is you switch x and y. And then the second step is you solve for the new y. And so to do that, I would add 3 first. And so x plus 3 equals y squared. And the opposite of a square is a square root. So you take the square root of both sides. Now, I want you to know something. When you add a square root that's not originally there, truthfully, it should come with a plus or a negative. It could be a positive or a negative. Now, in this case, since we restricted from 0 to infinity, we're looking at the positive side of the graph. So I would take the positive and not the negative square root. Okay? We restricted out the negative side. So I want to make a note of that I restricted out the negative side. Restricted out. So when we restrict it to the positive side of the graph, that negative's gone. That's why it's only positive. So once you get your equation, what you do is then you rewrite it using function notation. And so I would say f inverse of x is equal to the square root of x plus 3. And now it's a function if where, and you got to use the restriction. Now remember, originally we restricted from 0 over, but that was on the original function. On the inverse, it's going to be off the y's. So your x's are going to be from -3 and then all the way to infinity because it goes forever, right? So you could add in infinity if you want with inequalities. You don't have to include that. You could use that terminology, or you could say where the domain and you'd put the restriction instead of 0 to infinity, we would say -3 to infinity because that was the original range. It was down from -3 to infinity. And since we're switching x and y, we're switching domain and range. So this one's range becomes this one's domain. So that would be the restriction. Now, it says here on part C, question to consider. If the domain of f had been restricted to the left side, would our inverse in part B been the same? And the answer is no. It would not have been. The answer would have been, if we had restricted the other side, we would have had the inverse equaling the negative square root of x plus 3. And then the range would have still been from -3 to infinity though. The range, even though looking at this left side, it would have been from -3 to infinity. And so you'd include the same thing. Where -3 is less than or equal to x. Or, I'm just going to do quotes here to resemble all that. So that would be the same because the range is the same on both sides. Okay? Well, let's see this again. Now let's look at example 5. It says here, if the domain of g of x here is restricted to -infinity to 6, what is inverse be a function? Why or why not? Well, let's first think about this. I'm going to factor this to figure out where my zeros are to know what this graph looks like. So if I factor this, I need factors of 36 that add up to -12. And there's a lot of factors of 36, 1 and 36, 2 and 18, 4 and 3 and 12, 4 and 9. But the ones here I'm going to be using are 6 and 6. And to be a -12, it's a -6 and a -6. So what I have here is x minus 6 twice. This is g of x, so I could sneak in a g of x here. And I have that written twice, and since it's written twice, I could write it as x minus 6 squared. So what would that look like as a graph? Since that x minus 6 is on the inside, that is a horizontal translation, right 6 units, 3, 4, 5, 6. So I need to go right 6 here. And once again, I have a parabola. Just gonna draw a parabola rather than using the parabola tool this time. And so here's my parabola. Okay, we're at that point 6 to the right, comma 0. Now this says the domain is restricted from negative infinity until 6. So we're cutting off the positive side of the graph this time. So I'm ignoring that. That part's restricted out. Now, if that part's restricted out, does this pass the horizontal line test? And yes, this passes the horizontal line test with that part of the graph restricted out. Notice it would pass that horizontal line test because this part gets cut off. And so we would say yes on here. Why it is a function is I would say here, yes, the inverse of f is a function since every member of the range, you could say has or is mapped to one and only one member of the domain. So again, an inverse, what it does the opposite. So instead of mapping domain to range or input to output, it now maps output to input. And every member of the output, which is range, has one and only one member of the input domain. Okay, so now, if I had to find the inverse function, here's what I would do. I would actually use this equation. I think it'd be much easier. So since we found out that g of x, we found out that g of x was also equal to x minus 6 squared. Now remember, this represents the y. Y is g of x. Y is g of x. What I'm going to do is switch these as x and y. So I'm now going to say that x equals parentheses y minus 6 squared. And I'll go through solving that. That was step 1. This was switching x and y. Switch x and y. That's what I did there. And now step 2 is we solve for the new y. And so what I would do first step is I would take the square root of both sides. Just copy and paste that here. I'm going to take this. To get rid of the square, we got to do a square root. And so I'll take a square root of both sides. And now again, whenever you take a square root, you need to add a plus and a minus. But because of this restriction being on the negative side, I only want the negative. So the positive is going to be restricted out. Okay, this time the positive side got restricted out. And so I ignore the positive on the square root because I'm only looking at the negative side of the square root, or the negative side of the graph rather. And so picking up here, I would have negative square root of x, excuse me, equals y minus 6. And last step is I would add 6 to both sides. Negative square root of x plus 6, and that's not inside the square root because this is not inside the square root, equals y. And just like that, we have our equation. So I could write this as g inverse of x equals negative square root of x plus 6. And on our restriction, you could say it goes from a y value of 0 up until infinity, where x goes from 0 to infinity. So you could say 0 is less than or equal to x. You don't have to include the infinity when you do with inequalities, because if x is greater than 0, infinity is greater than 0, you don't need to write that. There's no upper limit. It goes on forever. So you write it like that. Or you could say where the domain is 0 to infinity. You could write it that way as well. Whichever way you like. Okay. Now with that, I'll let you try another one. Go ahead and try now DOL number 5 on the back of the packet. Try number 5. All right, example 6. Now let's start talking about some harder ones, some rational functions. Okay, rational is when you have polynomial divided by polynomial. This is where it can get a little tricky. And so I'm going to give you a couple of these to look at here. So let's just assume that the function will exist. And let's go through and solve this. Now remember, y is the same thing as f of x. So when I go to find the inverse, our first step again is to switch x and y. So I would say x equals y minus 2 divided by y plus 3. Now there's our first step. From here, what we're going to do is we got to do the opposite. So I have multiple y's to solve for, which means I got to combine those as one. And I'm going to go ahead and give you the trick on this. The trick when you have multiple y's is we're going to have to do a GCF at some point in time to make multiple y's become one y. To pull off a greatest common factor, I first need to get rid of the division. So I'm going to multiply by y plus 3 on both sides of the equation here. That's going to be my first roll. So those will simplify out. So I've switched for x. I switched my x and y. Now I'm on step 2. I'm solving for y. And so what do I have here when I distribute is I'm going to have x times y, and I'm going to have 3x. Now where did I get that? I just distributed y times x. I'm going to call it xy. I'll do alphabetical order, and then 3x. And that's going to equal y minus 2. And so here's the part that I want to note over is that I need to combine my y's to the same side of the equation to do a GCF. Okay, I need to write my steps in here in a moment. Let me pause this and add the steps. Okay, now that I added my steps so you can you can track with me here. What I'm going to do is I'm going to arrange for GCF. That's what I'm going to call this next step here, is I'm going to arrange for GCF of y. And the reason I'm doing this is I got to make two y's become one y. So what I'm going to do is I'm going to move this y's to the same side of the equation by subtracting y's. I'm going to do that opposite. And I'm going to do the opposite of adding a 3x because this 3x does not have a y. 3x. And so when I do this, what happens is I now have both my y's on the same side of the equation. I have x, y minus y equals, and over here, I'll have a -2 and a -3x. I'll put the -3x first. So now I can do my GCF. And that's the key to a rational function when you're finding its inverse, is to align your y's to the same side and do a GCF. So a GCF means you divide out what's common. So it's kind of like the opposite distribution. We're going to divide both sides. What we're going to do is divide out a y. That's the idea. So I'm dividing out a y. Now, mathematically, this would not be right if I wrote it that way, but that's the idea of what's going to happen. And so when I divide out a y here, I'm left with an x. And over here, when I divide out a y, I'm left with a 1. Now notice, if you distribute it back, you'd get this. GCF is the opposite of distribution. If I took y times x, I'd get xy. Y times -1 would be -y. So mathematically, I didn't change anything. That's why I say I should not actually show the dividing. But that's what you do. And so now the last step is I got to do one more opposite. The opposite of multiplying y times x minus 1 is to divide by x minus 1. And so that's how I'll finish this up. It's dividing by x minus 1. You don't have to keep the parentheses, by the way, on a rational. So when I rewrite this, I'm not actually going to write that parenthesis. So now that I have y by itself, and this was called the function f, I'm going to say the inverse f inverse of x is equal to -3x minus 2 over x minus 1. Now, remember the rule for domain. Since I never graphed this, to know where the domain exists, earlier it was x could not equal -3, and that's because you're not allowed to divide by 0. A -3 down here would be, when you add this 3, would give you 0, and that's why you're not allowed to do. On this one, x is not going to be allowed to be +1, because that's where you divide by 0, which means this graph, the y's would never equal 0. Since this one, the x does not equal, excuse me, I said 0, I meant 1. The y's in this graph will never hit 1, because this one, the x's never hit 1. And just like the x values here never hit -3, the y's value on this graph will never hit -3. Maybe I should just show you that in the graph. Okay, I'm going to type in the original graph. Okay, I want to go to new document, not going to save, and I'll just show you this. The equation was x minus 2 over x plus 3. That's my original function. And as it said on the problem, the graph would never hit would never equal -3. So I'll put that on there. You see the graph gets divided there. Well, what we just found when we had the inverse is that on the inverse, x does not equal +1, which means this graph also would not have a y value at 1. I think I need to go to 9 to make this red. Let me see here. Yeah, if you check that out, notice how, whoops, the y values never attained a value of 1. Okay, so now with that, I'm going to show you now the inverse. If I wanted to graph the inverse, what you can do is, let me pull up my equation here. And I'm not sure which one's green. I'm just going to try 4. I'm going to see what I get with 4. What I can type in is to know that I got this right, you could just switch the x and y and type in your calculator. So instead of y equals, I'm going to type in x equals. And then, so basically I'm typing in y minus 2, so I'm switching my x and y's, over y plus 3. And that right there is your inverse. Now to know if I got this correct or incorrect, what I would now do is you could check this, and this value, instead of being divided at x equals -3, it's now y equals -3. And instead of having y equals 1, it should be x equals 1 now. Should be the dividing. And I'm going to turn off this blue graph. And you'll see that these are the new asymptotes for that. And let's check our answer. The answer we thought this was going to be was, I'm going to get a color other than, let's do black. We thought that the answer should be -3x, where is it? -2 over x minus 1. When I hit enter, notice that that graph goes directly over the one we had for the inverse when I just typed in the inverse equation. So we did in fact do this correctly. These are inverses of one another. That is the correct inverse. And so now as I add this to the notes, you can see how what happens on an inverse is you switch x and y. And so if the original function never attained the x value of -3, then the inverse function will never attain the y value of -3. If the original function's y value never attained 1, then the inverse function will never attain the x value of +1. Notice that that's how the graphs break. This graph overlapped this because what I did here is I typed in this equation, but I just switched x and y. That's all I did here, and was able to graph the inverse, and notice that they overlapped one another. So let me show you one more before I give you one to try. Let's do this again. So again, remember the steps that we performed. The first step is we're going to switch x and y here. That's why the first step is to switch x and y. All right, and so I'm going to have x equals 2y plus 1 over y minus 3. And again, this is going to be when y cannot equal 3. You don't have to write that because we don't ever talk about restricting the range, but this would be true because this is where x does not equal 3. This is when the y will not equal 3. Now we go through the process of solving. So we solve for our new y second. Solve for new y. And so to do that, we're going to first multiply the denominator. We're going to multiply both sides by the denominator y minus 3. Sorry, my computer's going slow here. So I'm multiplying both sides by y minus 3. That's what I'm doing on this step. Let's see if I can slide this down and get it more aligned. Okay, so what happens when I do that is this denominator gets canceled by this factor. And so I'll distribute here. I'm going to have an xy. Y times x is the same thing as x times y. And I'm just going to go alphabetical order. And then I have a -3 times x. And that will equal 2y plus 1. And again, now I'm going to arrange for GCF. So I'm going to start arranging for GCF. And the GCF, we need to get our y's together. So it's a GCF of y. And so to do that, I need to move these two y's to the left with this xy. And I need to add 3x, since it does not have a y, to the left side of the equation. So those will simplify out. And I'll be left with xy minus 2y equals, I added the 3x, so I have a 3x and a 1. Let's do the 3x first. 3x plus 1. Now notice we can GCF. So now GCF the value of y here. So since they both have a y, you pull that out, and so what am I left with? I'm left with an x minus 2 when you divide out a y from here and a y from this term. I notice again, you can check with distribution. Y times x is xy, y times negative 2 is negative 2y. It's 3x plus 1, and now your last step is, since that y is multiplying, you divide by x minus 2. You don't need to you do not need to add a parentheses when you divide. The division itself serves as one, but I'll go ahead and put it there. So that would cancel out, and so that means since they call this g of x, I'm going to call this g negative 1 of x will equal the inverse of g will equal 3x plus 1 over x minus 2 when, and I can tell right now, this is easy to solve, x does not equal positive 2. So we now know the x and y value that this will not equal. We know that the y value won't be 3, and we know the x value will not be 2 anywhere on the graph. And so I'll just check this briefly here. Let me come back to my equations. F1, I'm going to change to 2x plus 1, 2x plus 1 over x minus 3. And I need to make sure it shows me the graph there. There's that graph. And I want to turn this one off for a moment. I'll come back to it, and I'm going to turn off the inverse for a moment. Okay, the original graph, we said x did not equal 3. And the y, get it from over here, since this was x does not equal 2, that means this y does not equal positive 2. If I look at that graph, you can see that that is indeed our original function. And everything's lined up like it should be. Everything's looking pretty good to me. Okay, there's our original function. Now let's find the inverse. So the inverse we had was 3x plus 1, 3x plus 1 over x minus 2. That's my inverse. I'm going to turn on the inverse, and I'm going to turn this graph off. That's my inverse, and we stated that the y value, the x value cannot be 2, and the y value cannot be 3. And as you can see, when you look at this graph, that is indeed accurate. Everything's lining up, everything's being divided out correctly. And just to show one more thing on there, I'll turn on that inverse line. I think it was relation 4, maybe. Let me go back and see. I think it's relation 4. There it is. I'll turn this one on. Oh wait, I got to change the equation. Over here it was it'll be x equals 2y plus 1. Let's make sure we got this right. And over y minus 3. And this will show us what the inverse should look like when I click that. Oh, it's acting like I made a mistake here. 2y plus 1, y minus 3. So somewhere in here, I might have made a mistake. Let me see here to get my equations in right. Let me pause and see what I did. Silly me, I just didn't press enter on it. Now when I highlight, you'll see it does highlight over it. I just hadn't pressed enter. It was graphing the old equation. So as you can see, that this inverse is correct. When I click that, it highlights what I have here. So that is, they're one and the same graph. more time showing them side by side, the original function where the graph never hit the x value of 3, the y value never attained 2. Over here, the inverse, x never attains 2, y never attains 3. Those are inverses one another. If you picked any point on this graph, any point whatsoever, so like let's just say that negative, it looks like approximately somewhere between -3 and 4, comma 1 exists, which means over here 1, comma -3 or 4 would exist, something over here, that points would be inverses one another. So again, you picked any point along this graph, it would have an opposite where the x and y point have been switched point over here. All right, with that, you can now try DOL number 4. Now that's a wrap. Go to your AP Classroom. There's 2 questions we have not done. I'm telling you to take a look at number 2 and number 6. Now, number 6, I'm going to give you a heads up. That's over a verbal description. And so just to give you an example here to think about, if I told you a function of students in the classroom, the students in the classroom is a function of time. The inverse, what you would do is you'd switch it. You'd say, well, time is a function of the students in classroom. You'd switch whatever was representing x and what representing y. It'd be the same with verbal. When you go to the verbal, that problem, you need to switch those, and you also need to think about a graph. You know, it tells you something. This is me just giving you some hints. It tells you that a function is decreasing. So what I would suggest you do, a decreasing function is something that's going down. Just make up some points that you think might exist and what that would mean for the inverse. If this is the function f here, let's call this function f, and it says it's a decreasing function, just make up some points. This might be 1, comma 8. Let's just say that's 1, comma 8. And let's call this one 7, comma 1. What would that mean is true for the inverse function? What would that mean is true for the inverse function? And just think about it. Plot the points, plot the inverses, I should say, and go from there. Okay, that'll help you solve number 6.